How's it going, everybody? So today we're doing a little bit of circuit theory. Specifically, we're going to be talking about the passive sign convention and power calculations. All right. Now, after understanding current and voltage, this is also paramount. Honestly, I like to say that there are four fundamental rules to all circuits. Kirchhoff's voltage law, Kirchhoff's current law, those are the first two, and the second two are passive sign convention and power. These four ideas, no matter what the circuit, all right, no matter what the circuit's made of, all of them always apply, and they apply to everything. Period. I mean, it doesn't matter what it is, and as long as it's electrical, it works. So, let's learn these two ideas. I don't know if you guys remember before, but I said earlier in a past video that current and voltage were not the same phenomenon. All right, they're not the same thing, and they're never to be confused. Now, current and voltage are like two halves of the whole that is electricity and, the phenomenon around it in itself. And I said that their equations, a voltage equation and a current equation, respectively, are different, and they can't be, confused. You can never put a current, an expression for current inside of a voltage equation. Now, I'm doing all this work to say that they're very distinguished, but of course they're also very similar. Naturally, it's almost like they come together. They don't always do that, but it's almost like they typically do. Okay? So that's where passive sign convention and power come into play. So current and voltage are in themselves separate, but passive sign convention and power actually talk about how they come when they come together. So passive sign convention is an idea. Straight up, it's just a convention that we use. And the idea is like this. Current flows from positive to negative. Okay? So if there's a voltage, and if I have an element and it has a voltage and a current, we like to say current flowing from plus to minus is the appropriate way to prescribe current flow. So I'm going to put a little check there. That's the appropriate way to have the current flow, I guess to say. It's naturally going to try to flow from plus to minus. Now, if you were to kind of look at some of these elements in this diagram, you're going to see that that's not always the case, all right? If I put a voltage and a current on this power source, the power source is going to have 10 amps coming out of the top of it and has 10 volts prescribed across it. All right. If I were to just kind of draw this blue arrow downward, then its current is certainly not going from plus to minus. It's actually going from minus to plus. All right. The same thing is happening here on this element 1. The 5 amps is passing from the minus sign of the 10 volts to the plus sign of the 10 volts. It's actually going, how I say, backward. If you look at elements 2 and 3, though, it is going in the right direction. This 15 amps is going to flow downward from the plus to the minus of the 5 on the element 2, and the same thing for the element 3. So on the element 2 and element 3, the passive sign convention is what I say, the way I like to say, obeyed. Okay? In this situation, when you have current flowing backward, it's going to flow from minus to plus. This is what we call a violation of the passive sign convention. Not to say that it's an impossibility. That's not the case. We just call it a violation of passive sign convention so that we can establish that this is negative. Something in this something out of these two quantities has to be negative. All right. So it's not both of them, but one or the other has to be negative such that the proper passive sign convention is actually happening. Now, what this means with respect to what's happening on a circuit is if this and this, the source and the element 1, both are disobeying passive sign convention, then either the 10 amps, the 5 amps, the 10 volts here, or the 10 volts there, one of those or two of those four have to be negative, all right? So either the 10 amps or the 10 volts has to be negative on the power source, or the 5 and the 10, the 5 amps and the 10 volts on the element, one of those has to be negative, all right? So what do I mean by that? I'll put a negative on my eye. If you look down at the bottom of the page, you could put a negative on the eye, and that would satisfy passive sign convention. Basically, when you say negative is on the eye, then what you're really saying is I is supposed to actually travel in that direction. I guess I'll do it in black, signifying that is where the negative came from. I would supposed to be flowing in that direction. All right, that's what the negative really means. Or you could put it on the negative, you could put the negative on the V, which means that, truth be told, the voltage is supposed to have a polarity like that. All right, either way, if I put a negative on the V, then I'll have the I going that way, and I'll have established passive sign convention properly. Or If I put a negative on the I, then I'll have the I following in the opposite direction, excuse me, and I put the V on it as it's supposed to, and I will have established passive sign convention. So please, when you get a violation of the passive sign convention, don't think that you're going to put negatives on both of them. You're only going to need to put negatives on one of them. The one that you put it on is all up to the equations of voltage and current. All right, when you solve through them, it'll make itself known which one ends up being negative and which one ends up being positive. Okay, don't just go put it on any one. It doesn't work like that. The equations, once you've solved them, are going to tell you, oh yeah, this solves to be negative, which means that the direction as seen on the circuit, all right, because remember, the direction as seen in the circuit is not the end all be all. It may actually not be that way. All right. A lot of times your answers are going to be negative because your professors have built your circuits and described the directions of your voltage and current, in specific ways. Okay. So what I'm trying to tell you is what you see is not always exactly what's happening. And some of those are going to end up being negative, which means that technically they're actually running backwards in real life. Doesn't mean you're going to erase them. All right. It just means you're going to put a negative on them to say that, in real life, this is actually going in the opposite direction. All right. So let that be passive sign convention. I'm going to let you guys know. I'm going to put a little star here on passive sign convention. After students have understood well the concepts involved in circuit theory, if you've messed up an answer, I'm 85% sure it's because you've messed up passive sign convention. Passive sign convention is a doozy. This little pictorial idea that I've written down here is great, but I like to think of passive sign convention as coming in one of two ways. I like to say the visual representation or the algebraic representation. So if you can clearly see, like on this case right here, that the passive sign convention is backwards, great. When you're doing your equations, you're going to know that a negative is going to pop itself up naturally. But what happens is sometimes you don't see the passive sign convention. Sometimes things will actually be going in the proper direction as such, an I and a V. And when you solve the equations and ... it'll solve and tell you maybe I is negative. And that happens. Okay, that actually does happen. All right. And there's a reason for that. Not saying that passive sign convention has to be followed. I'm just saying that it's an idea that we use to establish to establish signs in our circuit so that things can mathematically solve properly. Now, in the situations where you can visually see that everything's okay, but algebraically it won't be the case, you'll have to actually introduce negatives inside of your equations based on situations that are happening in your circuits. And those are actually really, really tricky. So please heed my warning. Pay attention to passive sign convention. Direction of current and the polarity of voltage is huge. I mean, absolutely huge. Once you've understood all the fundamentals, if you mess up, I'm telling you, it's most likely because you've messed up on passive sign convention. It is so easy to mess up on that, and it's ever pervasive, all right? I mess up on it all the time, and I know what I'm doing, It's just something that happens. It's something that comes with the territory, all right? Sign convention gets everybody, professors and students alike, so don't let that get you. All right, so now that we've established passive sign convention, time to establish power. So passive sign convention tells you how current and voltage are symbolically attached to one another. All right, if you have an element and there's a voltage on it, the current should be going, from positive to negative. It should be, but that doesn't mean it will. Mathematically, power talks about how current and voltage are correlated. Power is defined, I guess I'll put P, is defined always as current times by voltage. Okay, that is the mathematical description for power, and it is defined in watts. So voltage is in volts. Current is in amps. I probably actually, it's funny as I never actually even mentioned that in my current and voltage video. Shame on me, but I guess I can say it now because it's just like the next video. Current is prescribed in amps. Actually, yeah, and voltage is described in volts. Power, when you multiply those two, you're going to get watts. Okay, always, doesn't matter what element it is, power is going to be equal to V times by I or I times by V. It doesn't matter. Does not matter the element, period. That's just how it works. All right, it's a fundamental idea that mathematically connects the two. Okay, so let's talk about the ramifications of power. Based on what we just learned in passive sign convention, we understand that voltage and current can be negative. Because voltage and current can be negative, the passive sign convention dictates that power can be negative or positive. Plus, I'll put a plus over minus. Okay, so let's see what happens. If passive sign convention is obeyed, so let's say we have this situation. When passive sign convention is obeyed, actually, you know what I'll do? I'll put it down here like this. I guess I'll leave it in purple. When passive sign convention is obeyed, I have positive and positive on both sides. Power is gonna be a positive quantity. Okay? When power is positive, we like to say that the power is being absorbed. Okay? Now, naturally, if you flip your passive sign convention, sometimes students say, oh, you know, can I just run on the idea that current flows from minus to plus as long as I do that in the whole circuit? Yes, you can. Remember, ultimately, it's just an idea that helps you get the mathematics down properly. As long as you say, oh, current is minus to plus everywhere in the circuit, your answers are actually going to be the same as mine would be. So, I mean, for those of you who want to be different about it, you can. I've had students do that. That's perfectly fine. I just don't recommend it because why would you give yourself more heartache on something that doesn't need it? But that's just a little disclaimer, side note. So when current actually goes from plus to minus, power is positive, and we like to say that's absorbed. When current goes from minus to plus, I guess I'll do it in red. When current goes from minus to plus, remember, there's a violation in the passive sign convention, and therefore one of these must be negative. So we got to say power equals negative. Right, because you're going to have a positive voltage and a negative current, or maybe a positive current and a negative voltage, depending on what happens. Either way, you're going to get a negative number times a positive number. Your power is going to be negative, and we're going to say that is considered delivered. Okay? So we've got delivered power and absorbed power, and that makes some sense. If I'm going to be giving you power, then I'm delivering, and if you're going to be getting my power, then you're going to be receiving or absorbing it. Okay, and that's how power flows inside of a circuit. All right, power is given away by sources, and it's typically absorbed, received by most elements. All right, some elements actually give power as well, but that's neither here nor there. Just want you guys to understand that passive sign convention affects power very fundamentally, and you got to understand that there's a direction to it, just like there's a direction to current and voltage. All right, directionality is huge in circuit theory. Now, with understanding that power actually can come plus and minus. All right, you also got to understand that just like current and voltage, power has its own mathematical rule. Okay, the sum of all power in a circuit, the whole circuit, spelled that wrong, and the whole circuit must be equal to 0. Okay. Basically what I'm saying is what is delivered must be absorbed. What's delivered must be absorbed. And that's the only way. You can never have net power of positive or negative quantity for any circuit. It does not make sense. You're basically saying for this whole circuit, once the power has been appropriated, I'm going to be gaining energy, or losing energy. It doesn't really work like that. That kind of violates conservation laws. Power is a conservation law as well. That's all the statement is saying. So the sum of all power in a circuit must add to 0. And that's kind of it when it comes down to passive sign convention and power. Passive sign convention, I put a star on because out of the 4 ideas, voltage, current, power, and it itself, passive sign convention is the one that people may mess up on the most. All right, don't let it catch you. So let's just kind of use this top circuit as a tiny little example to see how the power works and how to kind of prescribe it all together. So what I'm going to do is, let's see, we'll use, I have no idea. Let's use, actually, instead of being difficult, we'll just use black. Let's use black. And what we're going to do is we're going to map the power in this whole top circuit. So I'm going to say the power source, because yes, the power source counts as an element. For the power source, I'm going to put EL1, element 1, EL2, element 2. And this is how I always do my power maps. Well, I shouldn't call it a map. It's more like a grid. And element 3. Each of these things are going to have a power associated with them and a voltage associated with them. All right, so I'm going to say there's a voltage for each. God, this is so messy. It's all good, though. As long as you understand, I'm happy. There's a voltage associated with each. There's a current associated with each. And there's a power associated with each. Okay? So, with that being said, I'm not going to put any, tricks inside that would require that you evaluate the current and voltage loops. That's going to happen. All right, if you look through our next example, you're going to see that there are situations where you need to do KVL and KCL to describe which voltages and currents are positive and negative. In this case, let's just assume everything is mathematically correct in terms of currents and voltage. So what we see is what we get. So let's see. The power source has 10 volts running across it. And it has 10 amps running across it. Element 1 has 10 volts running across it and 5 amps running across it. Element 2 has 5 volts, I'm saying running across it, 5 volts sitting across it, and it has 15 amps going through it. Element 3 also has 5 volts, and if you pay attention to that 15 is passing through element 2 and element 3, so it also has 15, okay? So those are our values. Now when we calculate our power, we've got to say I times V. But the thing is, you've got to make sure that you put negative or positive. So if you look at the passive sign convention on the current source, the current, if you kind of extend that arrow, is going from minus to plus. Because the current is going from minus to plus, I'm going to say the power is equal to negative 10 times by 10, which is going to give me a negative 100. Negative 100 watts, which is also like saying I have 100 watts being delivered to the circuit. And that makes a lot of sense. A lot of people get screwed up on sources because they say, well, sources violate passive sign convention. Yes and no. All right, I probably should give a lecture on how sources don't really violate passive sign convention, but mathematically they do. Think about it. You want a source to deliver power. Therefore, you would expect it, or it should have negative power associated with it, because you want that power to be being delivered. All right, that is actually what we've just done here in terms of the power on the source. Is a very, it's actually the most common situation of power for sources. Sometimes sources do absorb, all right, but more often than not, they're actually going to be on the delivering end of things. Okay, so that is how I will calculate that one. And I'll put a negative on it because it visually violated the passive sign convention. Remember I said your values, your currents and voltages, they're all going to be assumed to be proper and positive. Then when I do the passive sign convention, when I do the power, I have to look at visually and verify the passive sign convention. All right. So let's look at element 1. Element 1 is going to be 10 times by 5. Okay. But element 1, if you look at it, it's violating the passive sign convention. So what I have to do is I have to put a negative in front of it because it's going backwards to everything. So element 1 has a negative 50 watts, or 50 watts being delivered. Okay. You know what I should have done? I think I'll do it now because it's all good. What I'll say is I'll say this. I'm going to actually hold on. Let me go backward. There we go. What I'm going to do is yeah, this is what I'll do. Sorry for the little hiccup here. I'll flop the polarity on this 5 volts, and it's okay. It's okay because the magnitude has changed. But what I'll do is I'll put a negative 5 on this voltage source, and that's gonna just show you what happens when it's not a visual passive sign convention mix up, but a algebraic one. All right. For element 2, I've got 5 volts, and I've got 15 amps. All right. And the thing is, that current is violating passive sign convention because it's going backwards to the voltage. It's going from minus to plus. But the thing is, that voltage was negative 5. Negative 5. And I have to put a double in there. That happens. I want to show you guys that. You can get negative on top of negative. All right. So you take the idea that because the passive sign convention is backward, I put a negative on the outside of things. And also, that's my first one. And also, because I put a negative voltage in there, I have to put a negative voltage, in my equation. So I really do end up with a double negative. They will cancel. And what I will end up with is 75 watts. And they're positive. Therefore, it's 75 absorbed. And that's how that has to be done. So I just wanted to show you guys that you'll be sticking in negatives past just seeing if the passive sign convention is obeyed properly. All right. Now, unfortunately, I can't change any of these numbers because these numbers will give me the proper answer. If I change any of them, they'll kind of screw me up. But I just wanted to show you guys that you can't have negatives and positive go inside of it. So even if passive sign convention is being obeyed, if I get a negative voltage, all right, or a negative current, then the power will still end up becoming negative. All right. The final one will be 5 volts times by 15. All right. Now, because this situation is 100% proper, I don't have to worry about putting any negatives on top of it. And I get a 75 watts is positive and therefore have 75 watts absorbed. All right. So, with that being said, once you've done this little power chart, you're not done. You have to do this last step. You have to verify if the total gives you 0. If your total doesn't give you 0, then you made a mistake somewhere, and I'm pretty sure that mistake was in the passive sign convention. All right, so let's just add them up. I got 100 delivered. I guess I'll say minus 100, minus 100, minus 50, plus 75, and plus 75. Well, the two 75s are positive. They give me 150. The negative 100 and negative 150 give me a negative 150. When I add all these numbers up, I get 0. Because I get 0, I know that my power calculations are right. Only when your powers are 0 added up for everything will you get a proper answer. All right. If I would have added them up and got a net answer of either positive or negative number, then my answer is wrong. It doesn't matter what you tell me. It has to be wrong because you have to have this power statement be satisfied. It just has to be. Okay. So let this serve as a tiny little example for passive sign convention and power. I hope you guys understand the concept behind passive sign convention and power in itself. Power is an idea. Well, power is a phenomenon. We actually measure the power in our devices. Remember, power is made up of two halves, current and voltage. All right, remember I said voltage and currents make up two halves of the phenomenon. The phenomenon you could also think of as the power stored in an electrical situation. Excuse me. And passive sign convention is just something that it's just an idea that we use to establish mathematical or sign continuity, if you will. Okay. So with all this said, we got a couple examples that we can look at here from here on. I hope this all helps.